Assalamualaikum and hi, my name is Sophia with the ID number KA25006 and I'm handling the scenario, also the assumptions.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Fatin Shamina, KA25005, and I will cover the 2D schematic and vector mapping.
Assalamualaikum, my name is Afarin Safira, ID number KA25007, and my part is calculating centroid.
Assalamualaikum, my name is Sharifa Maisara. My ID metric is KA25002. My part is going to calculate the equilibrium. Thank you.
Okay, everyone, so welcome to the podcast. So for our statics project, we're going to deep dive into the mini hydraulic stepper like this one. So honestly, it's a whole mode counts, as you guys know, right? Our mission is to find the internal forces, which is the AX from the hinge, AY also from the hinge, and F cylinder thrust, which is when the machine under a standard load. So we're focusing on a static hole, which is 50 kilogram user, roughly like 490.5 Newton pure force, just like vibing in a mid-stroke hole. And then the math actually makes sense when we're doing the assumptions. So what are the assumptions? The first one is rigidity. We're assuming this machine is built different, like no bending, no flexing, and whatsoever. And the next one is frictionless pins. We're treating the hinge points like they got zero friction. So we can focus on the pure reaction forces, which is the AX and the AY. And the third one is the weightless members. What are the members? The members are actually the pedals. So since the users is 50 kilogram, the weight of the plastic pedals is really negligible. It's just a noise in the data. So we're setting the stage for total structural integrity. And now Fatin is going to show you the receipts of the free body diagrams.
Okay, so let's talk visual. So to see really what's going on, we had to deconstruct the stepper into two separate FPDs. First, we look at the pedal FPD. We got the user living its best life pushing down, while the hydraulic cylinder is pushing back at a 52.48 degree angle. So because that cylinder is angled, it's not just pushing up, it's low-key trying to shove the pedal forward into the hinge. So that's where the AX comes in to keep things balanced. So then we move to the base FPD, and this is where Newton's third law really enters the chat. Every force from the pedal get passed down here, but in reverse, total action reaction energy. We also can't ignore the resistance bands pulling at 65 degrees. They are adding a lift and a slide component that the floor has to deal with. So my diagram maps out how the machine stays grounded using a single end floor and enough static friction to keep you from sliding across the room while you are working out. If the vectors don't align, the whole thing flops. So next, let's get into geometry with.
Okay, next we have to determine the centroid. As you can see from the diagram, we can divide the object into 8 shapes. All of them are rectangles except B, that is a triangle, and G and H, that is a right angle triangle. So first, how do we calculate centroid? First, we have to determine the area for each part, and then we have to find the X and Y. Then we have to determine the total area and the total of area multiplied by X and the total of area multiplied by Y. So we can get the X bar, that is the total area multiplied by X over the total area, and bar Y, that is the total area multiplied by Y divided by total area. So the volume will be 15.16 cm and 6.11 cm. Then after that, we have to determine the pin curvature radius. Okay, so for this radius, I identify the pin coordinates to be at the origin. Then from that, we can calculate it by having the X bar minus the X coordinate plus Y bar minus the Y coordinate under a square root. So the final distance will be 16.35 cm. Lastly, we have to understand the tipping point analysis. So as we can see from the base, the distance is 43. We divide that by 2. From that, we can find the center, and from the center, we can since it is at the x-axis, so we divide the half value, that is 21.5, minus the X bar, that is 15.16. Then we have 6.34 cm, and the 6.34 cm will be the stability margin, which means that the object will not tip over itself, as the base does cover that margin. Next, we will go to the calculations.
So this is our FBD for the pedal. Now our goal is to find the AX, AY, and the force of the cylinder. So how do we do it? First, we have to do the moment. We will use the point A, which is here. So this one is a negative because it is clockwise. As you can see from the width of the person, if you compare it from the distance, from here, the distance, it will go clockwise, so it will be negative. And now for the W pedal, the width of the pedal, if we compare, it will also go to the clockwise, so it will be a negative. And then for the F cylinder, the force of the cylinder, cos. For our theta, it is found that our theta is 42.48. 42.48. So if you want to see if it's negative or positive, this will be the F cylinder. If we do it, it will be clockwise, so it will be negative as well. And then the F cylinder, Fy cylinder. So if we compare with the A, since it will be connected, it's not connected, it's basically at the same distance of the A, it doesn't have distance. So when it doesn't have distance, it will be 0. Alright, now let's put our value, negative 4.525, 255 cm, 2943. Negative F cylinder. And we will get our F cylinder 7.509 equals to negative 66,710. And then F cylinder, we will get 893.6 N. So that's our value for F cylinder. Now how do we find the AY? So let's erase this for the AY. Okay, so we have AY with the pedal, with the person, and the cylinder force. 952. Now for AY, now what's our value? So our value for AY will be 8434.07. There you go. And now that we have our AY, let's find our AX. So I'll here. Now let's do AX plus F cylinder cos 0. 6 cos. For AX, we will find it found. The value is 25.4. There you go. Now we have found our AY and AX and F cylinder. We have settled for our free body diagram for the pedal. So now we move on for the free body diagram of the base. Just now we separate the base and the pedal because we act it as if it's two components. We separate. Just now we separate the free body diagram of the pedal by 2, and as well as the free body diagram of the base. This is half of it. Okay, this is half, not the whole thing. It's half. So now what's our goal here? Our goal here is to find the end of the floor, and the tension of the. Wait. Oh, sorry. Not the tension of the band. The friction. Okay, now so how do we find the friction? So first we will use total of Fx. Now negative Ex minus F cylinder cos theta, cos 65 plus F equals to 0. Now let's put our value. And from here we can find our total friction, which is negative 1.134 N. Now we find our friction. Our next goal is to find the value and value, so we'll use the total of Fy. So negative Y minus the value of the base, F cylinder negative sin theta plus 10 plus tension. Now let's find our for the was 44.07, the value is 44.1, so that's the value, and our base is 196. And then we found that our F cylinder was 893.6. We saw the potential value is 50N. So now that we have found our value, we can find the value of N. So it will be 526.7. And there you have it. I think that's all for the calculation. Thank you for watching.
So guys, we're ending our podcast today, and see you soon. Bye guys. ASMR. Meet. See you soon.